So this stats review is on discrete random variables, kind of divided into two sections with binomial probability and geometric probability. For binomial, you have to have a set number of trials. You're going to do something a certain number of times. You can only have a success or a failure, and the probability of a success has to be the same for each trial. Everything that's highlighted is on your formula sheet. If you'll take a second and find your formula sheet and look at these formulas and look at where they are on your formula sheet so you can kind of get in the habit of where they are, because that's where they're going to be on the AP test. And we'll go over all this stuff, but the probability of a specific number of successes is NPK. N is the number of trials you're going to do. P is the probability of a success, and K is the number of successes I want. Always use the basketball example. I'm going to shoot a basketball 5 times. What's the probability that I'm going to make 6 of them? So 10 would be my N, 6 would be my number of successes, and the probability is of the probability of me making a basket. So I'm really bad at basketball, so it's probably really low. When you binomial CDF, your NPK stays the same, but this is the probability of having less than or equal to a certain number of successes. The average and the standard deviation, again, are on your formula sheet. Geometric probability will be on your AP exam, but there's nothing about it on your formula sheet, so this stuff you have to memorize. You do not have a set number of trials. It finds the probability of the first success on a specific trial number. What is the probability that I'm going to make my first basket on the 5th shot? So I want X to equal 5. I want it to my first success to happen on the 5th shot. So I want to fail, so that's my Q, and then K minus 1, so that'd be 4. So I want to fail 4 times, and then I want to succeed once. So if you think about that formula logically, it's not that hard to memorize. When you do geometric PDF, which finds the same thing, so you're going to use this on a free response. You're going to use this on a multiple choice. Free response, you have to show the formula, you have to show your work. Same thing over here. You're going to use this on a free response, but you're using those guys on the multiple choice. If I want the probability that I make my first basket on the 5th try, it's just the probability that I can make a basket, and then I'm going to put a 5 right there. And this is the whole less than or equal to. And you need to be able to manipulate. So if I want this, you need to know that that's 1 minus that. If I want, no, not equal to. If I want this, then you need to know that that's 1 minus that. So think about those and make sure that you remember how to do that. We'll work on that a little bit today. The average or expected value is 1 over P, something you have to memorize. The standard deviation is the square root of Q over P. That's very rare, but I have seen it once or twice. But the average expected value, you need to know. Okay. So just to start off with a little bit of vocabulary, a variable is a quantity whose value varies from subject to subject. Height, number of email messages you receive per day, just a variable. A probability experiment, possible outcomes may be known, but whose exact outcome as a random event cannot be predicted with certainty in advance. And that's what we're using all this to predict. Okay, so you need to know the difference between a discrete and a random variable. Discrete is a quantitative variable that takes a countable number of values, something you can count. The number of email messages received in a day, the number of home runs per batter, the number of red blood cells per sample of blood, the number of students present in class, something that you can tangibly count. Notice that between any two possible values of a discrete random variable, there is a countable number of possible values. You may receive 10 email messages a day or 12, but you can't receive 12 and a half. So discrete means almost like distinct. A continuous random variable is still quantitative variable that can take on all the possible values in a given range. Weight is a good example. A person can weigh 150 pounds or 155 pounds or any weight in between those two, including really, really long decimals. Altitude of a plane, the amount of rainfall in a city per day, the amount of gas in a car, the weight of a baby, the amount of water flowing through a dam per hour. All of these are kind of fluid measurements and can have all these values in between. So that's continuous. Today we're going to just focus on discrete. A probability distribution of discrete random variable or discrete probability distribution is a table, a list, a graph, or a formula giving all possible values taken by a random variable and their corresponding probabilities. The probabilities always have to be in between 0 and 1, and the sum of all of those probabilities always have to equal 1. So here's a great example. Well, we've got all of our variables, and then these are all the probabilities of all these variables happening. So they can all be different, but they have to all add to 1. The mean of a discrete random variable is also known as the expected value, and that's really, really important because they're going to ask it like that. Find me the expected value, and it's denoted by E of X, and that's the same thing as mu. And it's the sum of all your variables times the probability of that variable, and it's all of them added together. Sort of like if you think about your GPA. So you take all of your grades, but you times that by the weight of the class. So a standard class or an honors class or an AP class have different weights. So think of sort of that like your probability. Variance has a formula, not really something you need to worry about. Remember that the standard deviation is just the square root of the variance. No big deal. Okay, so example 8. Sophia was recently promoted to assistant manager at a small women's clothing store. One of her duties is to fill out order forms for women's shirts, which come in sizes 6, 7, 8, 9, 10, 11, and 12. She would like to determine how many shirts of each size to order. At first, she thought of ordering exactly the same number of shirts for each of the available sizes, but then she decided against doing that because there might be a greater demand for certain sizes than for others. She looked up sales receipts from the past 3 months and summarized the information as follows. So what she's got, this is a discrete probability distribution. She's got the shirt size, that's your variable. And then she has the number sold. Now that's not a probability, but we can very easily turn that into a probability. The number sold, okay? This is a great free response question. Here are your 4 parts. Prepare a probability distribution of the number of shirts sold for each size. Okay, let's just talk about that one. So here we go. The total number of shirts is 901. Using this information, we can compute the probability of each shirt size being sold. The probability of selling a size 6 is 85 out of 901. So all they're doing is finding the probability for each size by taking the total number of shirts sold out of the total number of shirts. So now I have a probability distribution. And this is very discrete because you don't have a shirt size that's in between a 6 and a 7. And that's all they want for part A. This is another way that you could represent it, and this is a histogram. Probability distribution shows that 9% of the customers bought a size 6, 14% bought a size 7, and so on. Okay, part B. What is the probability that a randomly selected customer will request a shirt size of at least an 11? The probability that we are at least an 11. Okay, so that means there. Okay, so if this was a free response, this is what they'd want to see. Number 1, state what you're looking for. I want a shirt size of an 11 or 12, and you're welcome to do that like that. Well, that is the probability of a shirt size 11 plus the probability of a shirt size of 12. And then I would even show, make sure you can show where those numbers come from, and then just add them together. So that's the probability that a customer will request a shirt size of at least 11. Part C. Compute the expected, there's your word, shirt size of a random shopper and the standard deviation of the shirt size. Okay, mu, expected value. Show them both. Always show them both, especially when it specifically asks for expected value. Okay, so I'm doing the average. So I take the shirt size and I times it by its probability. And then I take the shirt size and I times it by its probability. And I add them all together. And it shows that the expected shirt size is a 9.09, or roughly a 9. And again, go 3 decimal places. Standard deviation, no, you don't need to worry about that. Okay, D. If Sophia plans to order a total of 1,000 shirts, how many shirts of size 8 should she order? Okay, well, let's look at size 8. Got a 15% chance of somebody coming in and asking for an 8. So from the probability distribution, the probability of an 8 is 15%. Therefore, if I'm going 1,000 shirts, 15% of them need to be 8. That gives me 150 shirts of size 8. So you can see how they sort of took a sentence, inserted a couple little math formulas in here, and got the answer. Okay, so say what you got to say, get in and get out. Don't ramble, but make sure you cover everything. All right, combinations. A combination is the number of ways R items can be selected out of n terms of the order selected if the order selection is not important. It is denoted by n choose R. Here's how it's computed. This is not on your formula sheet, but you need to know it because if it's a free response, you need to be able to do it by hand. So n factorial over R factorial, and then subtract the 2. Factorial. Also a nice little button on your calculator that does this for us, if it's multiple choice. For any integer greater than or equal to 0, n exclamation point is read as n factorial, and it's computed as n times n minus 1 all the way down to 1. So 3 factorial is 3 times 2 times 1. 5 factorial is 5, 4, 3, 2, 1 multiplied. 0 factorial is 1. That's your special case. So a teacher wants to choose 2 students to represent the class in a competition. She finds that there are 5 students in the class who meet eligibility criteria. Because all 5 are eligible, she decides to select 2 at random. In how many different ways can this teacher select 2 students out of 5 students? Now again, order doesn't matter. Like if I have Calvin and Sung, then a group with Sung and Calvin, it's the same group. So I don't need to worry about order. I just need how many different combos. Well, here she is finding it by hand. And so the answer is 10. There are 10 different ways to select 2 students out of 5 when the order is not important. But using a combination function, you can do the same thing. So this is 5 choose 2. So 5 factorial, 2 factorial, and then 5 minus 2 is 3, so 3 factorial, and then you can cancel, and that's 20 over 2, which is 10. You can also do this on your calculator. It's under math, probability, and you just do 5 choose 2. So it's the number that you have total, and then how many people do you want to choose? So 5 choose 10. Okay, a bowling game. This would be a great multiple choice. In a bowling game, the pins are numbered 1 to 10 as shown. Suppose that following the first roll, 3 pins arbitrarily located are knocked down. So 3 pins get knocked down. I don't know how. In how many combinations can the remaining pins be standing after the first 3 have been knocked down? Okay, so I'm going to knock down 3, and I can knock down any 3 I want to. So I'm going to do 10 choose 3. So 10 choose 3 would be 120. That should be 10 factorial. Another way you could do this, you could do 10 choose 7. It's the same thing because it's 10 and then 7 and then subtract the 2. So you could choose how many different ways are there for the 7 pins that are left. What order can they be left in? So I can do 10 choose 3 or 10 choose 7. Binomial distribution. One example of a distribution of discrete random variables is the binomial distribution. A binomial distribution occurs in an experiment that possesses the following properties. There are n repeated trials. All trials are identical and independent. Each trial has 2 possible outcomes, known as a success and a failure. The binomial variable x represents the number of successes in n trials. And again, this is what's on your formula sheet. So this is the probability of x successes in n trials. So I'm going to shoot the basketball 10 times, and I want 3 successes. So P is the probability of a success to the n, and then 1 minus P, so that's your failure, and then n minus x. Sorry, that's an x, not an n. Where P is the probability of a success in a given trial. The mean of a binomial random variable is NP. So N is the number of trials, and P is the probability of a success. Variance. Now remember, variance is sigma squared. Not really something you need to focus on, but you do need to know the standard deviation. So that's just the square root of NPQ. Some examples of binomial random variables. A quality control inspector takes a random sample of 20 items from a large lot, inspects each item, classifies it as defective or non-defective, and counts the number of defective items in the sample. A telephone survey asks 400 area residents selected at random if they support the new gasoline tax increase. The answers are recorded as yes or no. The number of persons answering yes is counted. So feel free to pause it and read through the rest of these, but they're very straightforward. There's a success and there's a failure. But don't think you can only have 2 cut and dry outcomes. I can roll a die and still be binomial, even though there's 6 outcomes. If I roll a die and I want the probability that I'm going to get a 2, then getting a 2 is my success. And getting a 1, 3, 4, 5, or 6 is a failure. So I still have 2 outcomes, a success and a failure. But the probability of a success is different than a failure. Success would be 1/6, and a failure would be 5/6. The shape of a binomial distribution depends on the values of n and p. We did one with some candy out of a machine and the number of orange M&Ms or something, I think, and we messed with the numbers, and you saw how the distribution can change. And that's what this is going through. Pretty straightforward. Nothing to really... And you can see, and this one's really good, but you can start to see this is binomial. And again, remember, there are no numbers in between here. There are no values in between here. So these are very distinct bars, but you can see that it starts to become normal. And that's when we start to do a normal approximation of a binomial distribution. And that happens here in a little bit. Okay, let's look at example 11. Suppose a family eats frequently at a nearby fast food restaurant. There are 3 possible toys, a car, a top, or a yo-yo, given with the kids' meals. The toys are placed in the meal bags at random. Suppose this family buys a kid's meal at this restaurant on 4 different days. What's the probability that exactly 3 out of 4 meals come with a yo-yo? Okay, let's look down here at solution A. Each kid's meal produced is viewed as a trial with 2 possible outcomes, a yo-yo or not a yo-yo. Let's consider getting a yo-yo a success. Then getting a yo-yo, the probability of it is 1/3. So the probability of getting a yo-yo is 1/3 because there are 3 toys. Now, we're going to buy 4 meals. Therefore, we have 4 trials. So N is 4. Then here we go. The probability of 3 successes out of 4 trials. So I'm going to go there 4 times, and I want 3 successes. So 4 choose 3. Then I've got the probability of a success and how many of them I want. And then the probability of a failure and how many of them I want. So 1/3 to the 3 and 2/3 to the 1. And that gives you this nice decimal. So that's the probability that exactly 3 out of the 4 meals will come with a yo-yo. And if it's a free response, you have to do it by hand. You have to show the formula. If it's multiple choice, then you can totally do this on your calculator. Binomial PDF, NPX. N is the number of trials, P is the probability of success, and X is the number of successes you want. So I'm going 4 times. I have a probability of success of 1/3, and I want to be successful 3 times. Type that in, boom, got your answer. That's if it's multiple choice. Okay, part B says the probability that I'm going to get at most 2 meals. Okay, now I think of that as this, at most 2 meals, so 0, 1, or 2. If this is free response, you have to show all 3 and add them together. If it's multiple choice, this is when you do CDF. So the probability that X is less than or equal to 2 is binomial CDF, number of trials, probability of success, and whatever that number is. But remember, CDF only does less than or equal to. So if your setup is not less than or equal to, you have to be able to adjust, which I think we do on the next one. Okay, so I want at least 3 meals. Okay, so if I'm by hand, if this is a free response, I have to show at least 3. So that means 3 or 4. So I have to show both and add them together. If I'm multiple choice, the probability that X is greater than or equal to 3. Okay, I have to turn this into a less than. So I'm going to do the not of this. So 0, 1, 2. Okay, so this is what I want. Okay, so that is 1 minus this, this, and this. So the probability that X is less than or equal to 2. Okay, now here's a what if, because I don't think this covers one of these. What if I wanted this? Well, greater than 3 means I want 4 successes. So the not of that would be him, 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 and him. So less than or equal to 3. Remember, it's binomial, so there are no numbers in between. So if you want to be greater than 3, then you got to be a 4. So I need to 1 minus this guy, this guy, this guy, and this guy. So just be careful and make sure you're comfortable with that. And that's what the homework will help you do. D says, what is the expected number of yo-yos when 4 meals are purchased? And E wants the standard deviation. So D, the expected value is NP. So N is my number of trials, P is the probability of a success, and I get 4/3 or 1.33. Very, very, very straightforward. And again, we're not going to mess with the standard deviation. Although it's very simple, it's just the square root of NPQ. Okay, we're skipping that, and we're skipping that. And I think we go straight, go straight to geometric. Okay, geometric distribution is also discrete, but the setup is different. Geometric distribution occurs in an experiment where repeated trials possess the following properties. The trials are repeated until the first success is observed. So I'm going to shoot basketball until I make one, and then I'm done. All trials have to be identical and independent. Each trial has to have a success and a failure. That's what makes it binomial. But the point is, the big kicker is, and this great multiple choice question, no set number of trials. I could be out there shooting basketball for hours if that's how long it takes me to make one. Or I could go out there and hit the first one and be done. So X is not the number of, or like your N is the number of trials. Here, X is the number of trials required to obtain the first success. So here's the deal, and I don't like thinking of it like this. Think about it like this. I want to fail X minus 1 time, and then I'm going to succeed, and then I'm done. So I want the probability that I'm going to get my first basket on my 10th shot. That means I want to fail 9 times, and then I'm just going to succeed 1. So then I just have to figure out what the probability of me making one, and then you'll know the probability of a failure. The mean of a geometric random variable, this is not on your formula sheet, and you do need to know it. So that is something you're going to have to memorize. Mu, which is the expected value of a geometric distribution, is 1 over p. Let's see. Here we go, some samples. A worker opening oysters to look for pearls counts the number of oysters he has to open until he finds the first pearl. A supervisor at the end of an assembly line counts the number of non-defective items produced until he finds the first defective one. An electrician inspecting cable 1 yard at a time for defects counts the number of yards he inspects before he finds a defect. All right, so y'all get the picture. So number 12, let's go back to the fast food restaurant. Again, there are 3 possible toys with a kid's meal. Toys are placed in the bag at random. Suppose the kid in the family has her heart set on getting a yo-yo. So the family will buy him kids' meals until he gets one with a yo-yo in it. Find the probability that the family will get its first yo-yo with the 3rd meal. Find the probability that the family will get its first yo-yo with the 5th meal. And what is the expected number of meals needed to get a yo-yo? That's on average. Okay, so here we go. The probability that I'm going to get a yo-yo on the first try. No, sorry, 3rd try. So here I go. There's my formula. Now, that 1/3 of the toys are yo-yos. So 2/3 of the time I'm going to fail. I want to fail twice, and then I'm going to succeed. Now you can do this, always show your formula, and then you get your answer. Or you can do this on your calculator if it's on the multiple choice. It's just geometric PDF, 1/3, 3. So 1/3, the probability of getting a success, and the 3 is the number of trials that you want to go until you get a success. Probability of success, number of turns to get a success. Okay, B was having to purchase exactly 5 meals before getting a yo-yo, so I want to fail 4 times, and then I'm going to succeed once. Or I'm going to geometric PDF, 1/3, and I want it on the 5th try. Either way, you get the same answer. Grab your calculator and make sure you remember where geometric and binomial PDF and CDF are. The expected number of meals to get a yo-yo, 1 over p, but again, show it, mu equals e of x, 1 over p, so 1 over 1/3, that's the probability of a success. So on average, my expected number of meals I'm going to have to buy to get a yo-yo is 3, which makes sense. If there are 3 different toys, the expected number of meals you'd have to buy would be 3 before you get a yo-yo. All right, we're skipping this and all of that and going right down to here. Note on binomial and geometric distributions. In binomial distributions, the number of trials, number of meals purchased is fixed, and the number of successes is a random event. In the geometric distribution, the number of successes is fixed, but the number of trials to get the success is your random event. Okay, nice little note down here at the bottom. You can approximate a binomial distribution with a normal distribution only if NP and NQ are bigger than 10. There was one problem we did where we did it with a binomial distribution and then we used a normal distribution to approximate it and did like a normal CDF instead of a binomial CDF. And we showed that those two answers were crazy, crazy close to each other. But this has to be true. So who's N and who's P, number of trials, probability of success, number of trials, failure, and those two numbers bigger than 10, then you can use a normal distribution to approximate a binomial distribution. Binomial is all the different bars, and normal is your clean curve. Okay, skipping that, and skipping that. Okay, let's look at this. Inheriting blood type. Each child of a particular set of parents has a probability of 0.25 having a blood of type O blood. Genetics say that children receive genes from each of their parents independently. If these parents have, excuse me, 5 children, what's the probability that none of the children has type O blood? So if it's a free response, state what you're finding. You would state the formula ahead of this. Then I've got 5 choose O, probability of a success, 25% having type O, and I want 0 people to have it, and then probability of a failure, and I want all 5 to fail. Or I could binomial PDF, 5 kids, that's 5 trials, 25% chance of success, and I want 0 of them to succeed. Get the same answer. Probability that X equals 1, 5 choose 1. Now I want to succeed 1 time and fail 4 times. Exactly 3, 5 choose 3. Succeed 3 times, fail twice. Okay, look down here. Should the parents be surprised if more than 3 have type O blood? Okay, so this is more than 3. So that means the probability that 4 and 5. So this is 5 choose 4, succeed 4 times, fail once, plus 5 choose all 5. I want to succeed all 5 times and fail none. Type all that in, get your 2 decimals, or, and this is how you can manipulate this. If I want to be greater than 3, so here's 3. I want to be 4 or 5. Well, that's 1 minus the probability that I'm less than or equal to 2. No, less than or equal to 3. If I'm just greater than 3, then it would be less than or equal to 3. So this would be a 3. So 1 minus binomial CDF, because we're now in inequality, 5 trials, 25% success rate, and I want 3 to succeed. So if I want to be greater than 3, that's 4 or 5, so that's 1 minus less than or equal to 3. If I wanted to be that, then I'd be 1 minus less than or equal to 2, because I want to include 3. So now I'm just this one and this one. If I wanted to be that, greater than 2, well, that would still be 3, 4, and 5, so I would still be this. If I put the equal to here, then I would change this to a 1, because I don't want to be 2. I want the not of this. So think through those, and again, the homework's going to really help you go through those. Here's another one, free lunch. A local fast food restaurant is running a draw 3 get it free lunch promotion. After each customer orders, a touchscreen display shows the message, press here to win a free lunch. A computer program then simulates one card being drawn from a standard deck of cards. If the card chosen is a 3, the customer's order is free, otherwise he's got to pay. All 12 players are going to do this. What's the probability that exactly 2 of them win a free lunch? This would be a great free response question. I got 12 players. To draw a 3, probability is 4 out of 52. I want exactly 2 to get a free lunch. So I'm going 12, choose 2. Probability of success, I want 2 of them, which means failure. Make sure you see where that number comes from. And I want 10 failures. Or I can binomial PDF, because he's not an inequality, he's an equal to. PDF, number of trials, probability of success, how many successes I want. Then a nice little sentence here at the bottom. If 250 customers place lunch orders on the first day, well, here's another question. What's the probability that fewer than 10 win a free lunch? So now my N has changed. Probability stays the same, but I want fewer than 10. Well, fewer than 10 means 9 or less. So your CDF has to have an equal to in it. So less than 10 does not. So that means you hop down to 9. So 250 people, probability of success, and that's how many people or less I want to succeed. Questions may ask, would you be surprised if, are you convinced that? Find the binomial probability and justify your answer. I think we're good there. Okay.